Hello, my dear students. Today we will be discussing one new topic, and that is the variable mass system. Now, what is a variable mass system? So, suppose in any system, so this is your system, mass is getting added, or suppose the mass is getting ejected. So here the mass is getting added, and here the mass is ejected. So if either the mass is getting added to the system or the mass is ejecting from the system, then such system where the mass is changing with time is called a variable mass system. So here the mass is getting added, so you'll say that the rate of change of mass is positive. And here the mass is getting ejected, so you will say that the rate of change of mass is negative. So let us assume that the mass is added or ejected from a system at a rate alpha kg per second. So here you will write dm by dt is plus alpha, and here you will write dm by dt is minus alpha. Okay, and let the velocity of the added mass or the velocity of the ejected mass with respect to your system is given by v relative. Okay, so let the velocity of added mass with respect to the system is v relative. Then the force exerted by the system has magnitude which is equal to alpha multiplied by v relative. This force is called the thrust force and can be written as v relative dm by dt. Now, what is the direction of this thrust force? The direction of this thrust force is along the v relative if mass is added to the system. So if mass is added to the system, that means dm by dt is positive and the force is in the direction of v relative. Okay, and opposite to v relative when the mass is ejected from the system, because when the mass is ejected from the system, then dm by dt will be negative and the force will be minus of v relative alpha. So it will be in the direction opposite to v relative. So again I will write here F thrust is given by v relative dm by dt. So F thrust is equal to V relative dm by dt. Okay. Now again note V relative is again this I've already told you, but again I'll repeat. V relative is the velocity of added or ejected mass with respect to the system. So V relative is what? It is the velocity of the added or ejected mass with respect to the system. So here also I have written let the velocity of added mass with respect to the system is V relative. Okay. Now we will derive this relation. So let us suppose that at any time t the mass of your system is m. So let us draw the system. Let us draw this system. So this is at any time t, and this is, let us assign a different color. So at any time t the mass is m, and time t plus dt, the mass is m plus dm. Suppose the velocity is v. Suppose the velocity is v at time t, and the velocity becomes v plus dv at time t plus dt. Now for derivation, what we have done is we have assumed that the mass is ejecting. You can find also for if mass is added, but every time you will get the same answer. So we will derive only for one case when you will say that the mass is getting ejected. If the mass is getting ejected, dm has to be negative. The mass dm is ejected with relative velocity v relative, and here dm is negative. Okay, we will assume while deriving this, we will assume that the v relative is constant. So that means again I'll repeat what is v relative. So this mass which is getting ejected, this mass here which is getting ejected, so this mass here which is getting ejected, this mass is getting ejected with a relative speed. Relative speed means when you sit in the frame of this system, it appears to you that this ejected mass is moving with a velocity vrel. Okay, understood? So v relative is not the velocity of the ejected mass with respect to ground. So I will write it again for all of you. This v relative is not the velocity of ejected mass with respect to ground. But suppose you are asked to find velocity of ejected mass with respect to ground, then velocity of ejected mass with respect to ground is equal to the velocity of ejected mass with respect to the system plus the velocity of the system. So that means this is equal to vrel plus v system. Okay, so this v relative is not the velocity of the ejected mass with respect to ground. It is the velocity of ejected mass with respect to this observer which is sitting inside the system. Okay, so we assume one more thing that for deriving that we will assume is that v relative is constant. Okay, so now if there is no external force on this system, so we will, while deriving, we will take that there is no external force on the system, although the final formula that we will get is valid for any situation whether there is external force or not. So if there is no external force on the system, you will say that the momentum is conserved. That is, the momentum at this time has to be equal to the momentum at this time. Okay, so the momentum at this time has to be equal to the momentum at this time. So now again we have written here is what is written, velocity of the ejected mass with respect to the system is v relative. Okay, so the velocity of ejected mass with respect to ground is v relative plus v. Now see, in this diagram you will see that the initial momentum is mv. The initial momentum is mv, and the final momentum is m plus dm into v plus dv, right? Now see, your system contains total mass. That means the mass which was initially present and also the mass which is ejecting. So system contains the total mass. So initial momentum is m into v, but the final momentum here, look carefully, it is m plus dm into v plus dv. But this m plus dm is the mass of the remaining system, and minus dm is the mass of the ejected system. Why minus dm? Because dm is negative, because I have assumed that the mass is ejecting. So this is minus dm. Minus dm is the mass of the ejecting substance. Okay, so minus dm into, again see, listen carefully. Now when you are conserving momentum, you need the velocity of the ejected mass with respect to ground. So the velocity of this with respect to ground is how much? See, the velocity of ejected mass with respect to ground is v relative plus v. So you will write here minus dm into v relative plus v. Okay, in fact you can write minus dm into v relative plus v plus dv, but again dm into dv is very small, so you have to assume that dm multiplied by dv is very small. Okay, so we have neglected this. So we have neglected this, right? So now initial momentum is mv, has to be equal to the final momentum. So now momentum, by conservation of momentum, you will get initial momentum is mv, the final momentum is mv plus dmv plus vdm plus dmdv, but dmdv is assumed to be dmdv, I already told you dmdv we will neglect, minus dmv relative minus dmv. You will see that dmv getting cancelled, mv getting cancelled. From this you will get mdv is equal to minus dmv relative. But now we have also assumed that v relative is a constant. So now what I have done is we have divided it both the sides with dt. So you will write m dv by dt is equal to minus dm by dt into v relative. Now listen to me carefully. Minus dm by dt is the rate of ejection of mass, that is alpha. So you will say that uh, F thrust, this m dv by dt is called F thrust. This m is not a constant mass, this is a variable mass. So this is called F thrust, and it is equal to minus dm by dt is alpha v relative. So we have derived the relation that thrust force thrust force thrust force is equal to alpha multiplied by v relative. Thrust force is equal to alpha multiplied by v relative. Okay, so again I will explain it again for the students who have still having doubt. Okay, so system the system that we take is the total mass. The total mass means which includes all the mass, that is the ejected mass also. Okay, so at this time, at t time, the mass is m, the velocity is v, so the initial momentum is mv. Now because if you have taken the total mass, there is no external force, so the momentum has to be conserved. Now after time t plus dt, the mass becomes m plus dm. Remember, this dm has to be negative. Okay, and the velocity becomes v plus dv, right? So now the velocity of the ejected mass, with respect to system is v relative. But what is the velocity of ejected mass with respect to ground? It is velocity relative plus the velocity of the system. You can also write this as v plus dv, but you will neglect this. Why? Because in the final situation the velocity is not v but v plus dv. Okay, but we will neglect this. Why? Because dm into dv is approximately 0. So the final momentum here you will get, the final momentum here that you will get is m plus dm into v plus dv. But this is the this is not the total mass. That this is all. This is the mass which is getting ejected is also inside your system. So you will say that this this mass which is minus dm. Why minus dm? Because dm is negative. Why? Because it is ejecting, right? So minus dm into v relate, the velocity of the ejected mass with respect to ground is v relative plus v. Now by conservation of momentum you will equate these two, and once you equate these two you will see that, once you equate these two you will see that m dv is equal to minus dm v relative, since v relative is constant. So and what we can do is we can divide it by dt. So m dv by dt is basically called the thrust force, and dm by dt magnitude is alpha. So the thrust force magnitude, the thrust force magnitude is equal to alpha v page. This formula thrust magnitude is v relative by dm by dt is valid whether mass is added or ejected. Although we have derived it for ejected mass, but this formula is valid for any situation. So whether it is mass is added or means ejected. Now the direction of force, the direction of force is along v relative. Again I am repeating the same thing that we have discussed in the first page. The direction of force is along v relative if mass is added, and opposite to v relative when mass is ejected. The direction of this thrust force is very important. The direction of this thrust force on the system is very important. So what again I will repeat, this direction is along the direction of v relative if the mass is added to the system, that is dm by dt is positive, and it is opposite to the direction of v relative when the mass is ejected from the system. Okay, also this formula is valid even if there is an external force, although in this situation we derived the formula by using the no external force concept, but the formula for thrust force is valid even if there is an external force. Now what are the steps you must use to solve problems involving variable mass? So first step is make a list of forces acting on the main mass and then apply them on it. Then we will apply the additional force which is called the thrust force on the main mass, the magnitude of which is v relative dm by dt, and the direction is same as direction of v relative if mass is increasing and opposite to v relative if mass is decreasing. Then find net force on the body and apply F net is equal to m dv by dt. Then integrate with proper limits and you can find the velocity as a function of time. Now note, now in JEE you will see that most problems that they have asked in one dimension in variable mass is one dimensional. So you can replace this vector, you can replace this vector symbol with a plus or a minus sign assigned to vector quantities. You know that vector which is towards right will be taken as positive and the vector which is towards left will be taken as negative. So now that we have understood what is the concept behind the addition of thrust force or application of thrust force, now we will solve problems regarding that. So suppose you have a flat car which has mass m naught and it starts moving towards right due to a constant force F. Now the sand is spilling on the flat car from a stationary hopper. So sand is spilling, but this is stationary. This is stationary. So now in this question you can see that the mass is getting added. The mass is getting added. So first of all we will write V relative. What is V relative? So let at any instant, see at t equal to 0 the velocity is 0. But at t equal to any time t, the mass of the system has become equal to m naught plus mu t, because mu is linearly increasing. Okay, because it is given that it is rate of loading is constant. So at t equal to 0 the mass was m naught, at t equal to any time t the mass will become m naught plus mu t. Okay, so this is the added mass that we have drawn here. And suppose at t equal to any time t the velocity that the cart has attained is v. So v relative is defined as, listen carefully, v relative is defined as velocity of the added mass, the velocity of the added mass with respect to the system. Now you can see that the added mass is coming from a stationary hopper. So that means in this direction the velocity of the added mass is 0. So v relative is equal to velocity of added mass is 0 minus velocity of system is v. So that means v relative is equal to minus v. Minus means the negative direction. So v relative, you can see in this diagram we have drawn that v relative is towards left, right? Okay, now what we will do is, first that now that we have found out v relative and mass is getting added, so you will say that the thrust force is given by v relative, that is minus v into dm by dt, that is mu. So F thrust is equal to minus mu v or v mu, right? Minus means the direction is, minus means the direction is, minus means what? The direction is opposite to, sorry, in the left direction or the negative direction. So now let us draw the FBD of this system. So you will see that this was the external force, and because mass is added, it is the thrust force is in the direction of v relative, which is towards left. So the thrust force is in this direction, and the value of the thrust force is mu v, and the mass of this at any instant is m naught plus mu t. So you will write the net equation as F minus mu v is equal to m naught plus mu t into dv by dt. Okay, now what they have asked us, they have asked us find the time dependence of velocity and the acceleration of the flat car in the loading process. So here this dv by dt is the acceleration of the flat car. Okay, now what you will do is you will write variable separate dv upon f minus mu v, dv upon f minus mu v is equal to dt upon m naught plus mu t. Now at t equal to 0, you know that the velocity is 0. At t equal to any time t, you need to find the velocity. From this, what you will do, you will integrate and you will say that minus 1 by mu ln f minus mu v, integrate it from 0 to v, is equal to 1 by mu ln m naught plus mu t, integrate it from 0 to t. Mu getting cancelled out, and you will get minus ln of f minus mu v divided by f. I have put the limits. First we have put, instead of v you will put v, and or the lower limit you will put 0, is equal to ln m naught plus mu t divided by m naught. So from this you will get, if you take this minus inside, you will get, and you will get f by f minus mu v is equal to m naught plus mu t upon m naught. So from this you will get, f m naught is equal to f m naught, or you can say like this, f minus mu v is equal to f m naught upon m naught plus mu t, right? So from this you will get f minus, f common, we will take m1 minus m naught upon m naught plus mu t is equal to mu v. So from this you will get the velocity as a function of time is f by mu into m naught plus mu t minus m naught divided by m naught plus mu t. So here m naught getting cancelled out, mu will get cancelled out. So you will get the velocity is ft upon m naught plus mu t. So you can see I have written the answer here. Velocity comes out to be ft upon m naught plus mu t. If you want to find the acceleration, what you can do is you can differentiate this again with respect to time. You will get the acceleration. I will not do that. I have already written the answer here.